Hello everyone, we're Group A19, Diana Huang, Brandon Fahy, Mingming Jie, and Zangba Dangfa. We're going to talk about linear search and binary search today. So, first, we want to know why is search so important. We are actually doing search every day. Internally, like in your brain is always searching. Like for a face you have met before, or for some knowledge you have learned before, etc., etc. And externally, we're also always searching. Like you use Google or some other search engines to search for a restaurant we can eat at, for a party where we can go to, and for the clothes we want to wear today. Probably that's not on the search engine, but you're doing it every day. And also, you might be using library website to search for some resources that you can use for the paper. So, since we're doing it every day, then we need some good strategies for search. And today we're going to talk about linear search and binary search. They may not be the most efficient one, but they are very basic and relatively straightforward. So today we're going to first give some example. We're going to first give definition and some examples of the both search strategies, and then we will compare them for pros and cons. Now, Brandon is going to talk about linear search.
Checking every one of its elements one at a time in a sequence until the desired one is found. Now, what this basically means is that it's going to evaluate the first element in a given set or sequence, and it's going to determine whether or not that meets the search criteria. If it doesn't, then it will linearly proceed to the next element in the set. If that element matches the search data, the search ends. If it does not, it proceeds to the next linear element. Now, we see this, we have an example here, where if you have a set of all natural numbers, and you're looking for the number 6, you'll start with 1, and then it will determine whether or not 1 is 6, which it of course isn't, and then we'll proceed to 2, then we'll proceed to 3, then 4, 5, and then finally on up in 6, and it will return that search. That's a basic understanding of linear search, and now here is Mingming.
Hi everyone, I'm Mingming, and I'll be talking about binary search. So binary search is a searching algorithm, and it is used when there's a list that's already ordered in terms of increasing size. So this search works in this way. To find the integer x from a list of a1, a2, all the way to an, we first compare x with the sequence's middle term. And we find this middle term, which has the index of floor n plus 1 over 2. So if x is greater than this middle term, then x is restricted to the second half of the sequence. But if x is not greater than the middle term, then x is restricted to the first half of the sequence. So now the search is restricted to no more than half of the elements. We'll repeat this process comparing x to the middle term of the restricted list, and we'll continue narrowing down the sequence until only one term of the search remains. We then compare this remaining term with x to determine whether this term is equal to x. So here's an example. Let's find the number 8 in the list shown below. First, we figure out the middle index, m, and that will be the floor function of 9 plus 1 over 2, because this whole sequence is a total of 9 terms, and this is the index 5. So now we split the list at the 5th index. So we have two lists of 2, 4, 6, 7, 8, and then 20, 26, 34, and 35. So a5 is 8. And 8 is not greater than this middle term 8, so our search is restricted to the first half of the list, which is the first through 5th elements of the original list. This sublist is again split into two smaller lists of 3 and 2 terms, shown below. Because 8 is greater than the largest term of the first of these two lists, which is 6, the search is restricted to the second list. That list of two terms is split into two lists of one term each, so 7 and 8. Because 8 is greater than 7, the search is restricted to the second list, the list containing the fifth element of the original list, which is 8. The search has been narrowed down to one term. Comparing the remaining term with the term we are looking for, 8 is located as the fifth term of the original list. Here's another example where the element we are looking for is not in the list. So searching for 7 in the list 2, 4, 6, 8, 10, we first see that 7 is greater than 6, which is the middle number of the sequence. So our search is now restricted to the second sublist, which is 8 and 10. 7 is not greater than 8, so the search is restricted to the first list containing the fourth element, which is 8. Now the search has been narrowed down to one term, a comparison is made, and 7 is not equal to 8. Thus, the element we are looking for was not found. And now Samba will compare binary and linear search.
Hello everybody, I'm Samba, and I'm going to be comparing binary search and linear search. So first, what we need to know about linear search is it does not require the data to be sorted, whereas binary search requires the data to be sorted. Linear search also requires the equality comparison, which means that we know what we want, we're looking for, and we're only going to be saying if this equals to this, then if it equals to that, then stop. If it doesn't, and then we'll continue our search pattern. Whereas binary search requires an ordering comparison, which means that we're going to need a equal sign, less than equal, and greater than to accomplish what we're looking for. Here's a good example of searching. Let's say we're searching U in the alphabet and performing a linear search. First, we'll be looking at index 0 of the alphabet, which is going to correspond to A, and we're going to say, is that equal to U? No. We continue, and that's going to keep going until we hit index 20, and is that equal to U? Yes, and then we're done. So that's why linear search is sequential. It's by sequence. Now, if you decide to look for U in the alphabet using binary search, we're going to be using comparisons. So we're going to compare the index 12, which stores a M, and we're going to compare that to U. And since M is smaller than U, we'll look further on, and so forth. And we can see at the end that we're going to be comparing list of 20 to U, which is the same, and then we exit our search. That is also why we say in binary search everything is sequential. Also, the linear search complexity is of big O of n, because the average of linear search is n over 2, but the half is just a constant, so if we put that in a big machine or a fast machine, it wouldn't matter. That's why we just say it's complexity of big O of n. In binary search, the complexity is going to be of natural log of n, because we start off by dividing the list by 2, and so forth. And it's actually natural base of 2, but the base wouldn't matter either if you have a fast machine. Same concept, and that's why binary is of better performance. Alright, thank you for watching.